right, today's lesson is 4.2, which is properties of exponents and power functions. So an exponential function, which you probably are quite familiar with, has a variable as an exponent. So I just gave you an example, 2 to the x. X is obviously your variable. In a power function, which is familiar to you but not as recently talked about, the variable's in the base. So notice x is your base and your exponent is actually a number. And you probably know 3 cubed is 27. And you're going to be kind of solving for these today, so it'll be really keeping track of what's exponential versus power. In the work that you're going to be doing, you're going to have to recall all of your exponent rules. So whether they're really familiar to you or not, I'm going to kind of breeze through all of them. So I have just a couple examples to get you thinking about them, and you can always fall back to this if you don't remember the rules. So if I said take x to the 5th times x to the 3rd, if you expanded that, x to the 5th means multiply it times itself 5 times, right? So if I expanded that, x to the 5th would be x times x times x times x times x times x to the 3rd, which would be 3 more. Well, how many x's do you have altogether? So if you add all of those together, you have 8 of them. So this is equivalent to x to the 8th. Okay, same idea with 3 to the 7th times 3 to the 4th. Why did I pick such big exponents? But if I expanded that, I would write 3 times 3 times 3 times 3 times 3 times 3. That's 7 times 4 more, 3 to the 4th. So 3 times 3 times 3 times 3. And if you count all those up, you have 3 to the 11th. Well, if you generalize, what did we just do? Rather than expanding all that, because that's rather painful, if I go back to the original expression and I look at my answer, how are they correlated? Well, if you add the exponents, 5 plus 3 is 8. Same thing here, 3 to the 7th times 3 to the 4th. If I add those exponents, 7 plus 4, is 11. So if I generalize my results, if I have the same base, like x to the m times x to the n, notice they're both bases of x, however, I can just add those exponents together. So when you multiply bases, you add their exponents. Okay, rule number 1. Okay, what about when you're dividing? And I'll go through this one a little more quickly, but if I expand on this, x to the 5th is x times itself 5 times divided by x to the 3rd, so 3 times. Well, then if you notice here, these x's are going to cancel out. And what are you left with? You're left with x squared on top, 2 x's, right? Okay, same idea with 3 to the 7th. If I multiply all of those out first, and then I divide by 3 to the 4th, so 4 of those. Again, what happens? Well, these 3's are all going to cancel each other out, and I have 3 3's left in the numerator, so 3 to the 3rd would be my final answer. So if you see how this generally works, if I go back to my original expression, if I have x to the 5th divided by x to the 3rd, if I subtract those, 5 minus 3, I get my answer. Same thing with 3 to the 7th divided by 3 to the 4th. If I subtract those exponents, 7 minus 4 is 3, so I get 3 to the 3rd. So if I generalize these results, if I have any base divided by the same base, you can just subtract their exponents. So this will be equivalent to x to the m minus n. All right, next rule is a power on top of a power. If I expand this, I'll do it with the first one, maybe not the second one, but x to the 5th and then cubed means I'm going to do x times x times x times x, that's 5 times. And then if you cube something, you take it times itself 3 times, right? So I'm gonna just do that again. 1, 2, 3, 4, 5. And then I'm gonna do it again. 1, 2, 3, 4, 5. Well, how many x's do I have altogether? 15. Now that was kind of painful to expand that, right? But you always have that option to think about, like, what are you doing? Okay, I'm not going to expand 3 to the 7th 4 times because, you know, that just takes a while. But you can probably already see that when you have a power on a power, like x to the m, and then raised to another nth power, you simply just multiply those numbers together. Like 5 times 3 is 15. Okay, if you have a power within a product, a little bit different, so just be careful. When you have 2x to the 5th and then that whole thing is cubed, that means you're doing 2x to the 5th times 2x to the 5th times 2x to the 5th, right? I'm cubing it, taking it times itself 3 times. So now if you apply your prior knowledge, I'm really just taking 2 times 2 times 2, which is 8. And then x to the 5th times x to the 5th times x to the 5th. Remember, when you have the same base, you can add the exponents. So 5 plus 5 plus 5 would be 15. Okay, and same with a quotient. Again, I won't go through that one, but when you have a power on top of a product, so if you have like a times b to the nth power, you have to make sure that you distribute that exponent to both bases, right? So if you go back up to this question here, if I distribute the cube to the 2 and to the x, well, 2 cubed is 8, and power on a power I would multiply to get x to the 15th. So you don't necessarily have to write all of that out. Same thing with quotients. This, I'm going to cube the numerator and cube the denominator. So you carry that power through to absolutely everything inside. So this is going to be 3 cubed over x cubed, but 3 cubed is 27, so you could simplify that. All right, your remaining exponent rules are negative and 0 exponents, so I just wanted to give you a visual. If you expand on my powers of 10 here, 10 to the 3rd, you know, is 1,000. 10 squared is 100. 10 to the 1st is 10. Well, if you look at that pattern already, it's just taking away 1 0 every single time. So 10 to the 0, if I take away this previous 0, is going to be 1. And you probably recall that anything to the 0 is 1. But if you don't, there's your visual reasoning behind that. Now if I carry on this pattern, okay, so go back up here, I started at 1,000, and then I divided by 10 to take away 0. Now I'm at 100, divide by 10, take away 0. Now I'm at 10, divide by 10, now I'm at 1. If I keep dividing by 10, well, what is 1 divided by 10? It's 1/10. And if I divide by 10 again, I'm at 1 over 100. If I divide by 10 again, I'm at 1 over 1,000. Well, now look at your negative exponents here in correlation with this. If 10 to the 1st is 10, 10 to the negative 1st, I reciprocal that and I get 1 over 10. 10 squared is 100. 10 to the negative 2nd, if I reciprocal that, I get 1 over 100. 10 cubed is 1,000, but 10 to the negative 3rd, if I reciprocal that, I get 1 over 1,000. Okay, so again, your negative exponent rule, anything to a negative exponent means you're going to reciprocal and make it a positive exponent. In your textbook, you have on page 197 a summary of all of these. Okay, so if you get stuck, refer back to your book if your notes aren't good enough. So page 197 is a summary of all of these properties. Okay, you will kind of put all these properties together and do a problem like this. So if it says simplify using your exponent rules, take a look at this first. I just want to talk about all the options that you have. So first and foremost, this is clearly raised to a negative exponent. That's probably screaming at you the most, but maybe not. If I ignore that inside the parentheses, I could deal with, I have a k, a base of k, and a base of k. I could divide those. I have a base of x and a base of x, a base of h, a base of h. So I could subtract all of those exponents since I'm dividing. If you are comfortable with putting k to the first here and x to the first, I would highly recommend that so that you notice that every base has a power, an exponent. Like that's probably pretty important for you to notice. So you can start there, or you could take your negative first exponent up here and you could distribute that to everything inside the parenthesis, which is totally fine as well. Okay, I'm gonna hold off. I don't like to deal with negative exponents until I have to, so I'm going to take care of the stuff inside the parenthesis first, but you could do either, just to be clear. So inside the parenthesis, I'm going to talk about my k's first. K to the fourth divided by k to the first. Because I'm dividing, I'm going to subtract those exponents. So I will have k cubed left on top. Okay, then my x's, I have x to the first, and I have division of x squared. So if I subtract, and be really careful, 1 minus 2 is negative 1. When you subtract, your answer always ends up in the numerator. I'll come back to that negative exponent. Okay, then h to the third divided by h to the third. Well, 3 minus 3 is 0, and you might not even write that, and I get that, I might not either. Okay, and I just really have 1 left on the bottom. And then this whole quantity is still raised to that negative first power. Don't forget about that, right? So now, since I have all my bases combined, I'm going to deal with this negative first here, and it's a power on a power, so I'm going to distribute it to all bases inside that parenthesis. Okay, so when I distribute, I multiply the powers. So I'm going to have k to the negative third, x to the positive first, because negative 1 times negative 1 is positive, and then 0 times negative 1 is still 0. Okay, and then this is over 1 still. And then last but not least, I don't want any negative exponents. You should never have negative or 0 exponents in your answer. Okay, so k to the negative third. Remember, when you have a negative exponent, you reciprocal that. Well, how do you reciprocal that? In this case, you're going to bring the k cubed down to the denominator rather than the numerator and make it positive. X to the first stays where it is, and h to the 0, you know anything to the 0 is really just a big fat 1. So your final answer is right there. All right, on to solving. These are gonna give, I'm gonna give you some strategies for dealing with exponential bases to solve. Before I do that, I just wanna have you look at this simple example up at the top. So if I have 2 to the x equals 2 to the third, if both of the bases are the same, like 2, then you know their exponents as well have to be the same, because otherwise they wouldn't be equivalent. So logically, I know this one, x would have to be 3, because then 2 to the third equals 2 to the third, which is a true statement, right? 8 equals 8. Okay, now if you look at this example, 8 to the x equals 4. Well, my bases are not the same. So using the strategy from above, if I can get my bases to be the same, then I can just set the exponents equal to one another. So you need to decide, is there a common base between 8 and 4? And hopefully you would catch that they're both powers of 2. So 8, this base of 8 is 2 cubed. But then there's also an x up there, so don't forget about that. Okay, then this base of 4 is also a power of 2. 4 is 2 squared. So all I did was rewrite 8 as 2 cubed and 4 as 2 squared. Okay, and how is that helpful? Well, again, now that these bases are both 2, like a base of 2 and a base of 2, I know that their exponents have to be equivalent. So now I can just say, well, 3x equals 2, and then divide both sides by 3, so I know x is 2/3. And obviously you can check your answer. If you go back up here and do x to the 2/3 on your calculator, you should get 4. Okay, a little more tricky if you look at this example, 1/2 to the x equals 16. Okay, well, if you think about it, as I put positive numbers in for x, it's gonna get smaller. Like 1/2 squared is 1/4, 1/2 cubed is 1/8. I'm not gonna be getting bigger to get to 16. So to write this base of 1/2 and the base of 16 to be the same, they're both powers of 2. And what's tricky about this one is 1/2 is also 2 to the negative first, right? 2 to the negative first is reciprocal that 1/2. So 1/2 and 2 to the negative first are the same. And then because I have an x here, don't drop that x down there. Okay, well 16 is also a power of 2. 16 is 2 to the 4th. And now, again, that my bases are the same, then I know my exponents also have to be the same. So I can set negative 1x equal to 4, divide both sides by a negative, and I will get x equals negative 4. So really key to both of these questions, we're getting the bases to be the same. And you might have to, get a little creative. Okay, then we're gonna solve a couple power functions. So now notice that your variable is not an exponent anymore. Your variable is actually the base. So now we're into some power functions. So x to the 4th equals 3,000. You could totally guess and check this. What number times itself 4 times equals 3,000? But I don't really know. I mean, I could play around my calculator and try to get as close as I can, of course, right? Or if you think about it, how would you undo a 4th power? Well, you would do a 4th root. And we've talked about that with squares, right? How do you undo a square? You square root. Rather than doing that just for the sake of those that might have like an 89 calculator, that it's not as easy to just 4th root something, I'm gonna think about reciprocals in terms of exponents. So if I have a 4th power, if I could raise that to the reciprocal power, which is 1/4, right? The reciprocal 4 is 1/4. Then my exponent rules say power on a power, I would multiply. Well, what is 1/4 times 4? That's just 1. So I eliminated that 4th power by raising it to its reciprocal power, right? But of course I have to balance the other side. So now I'm gonna take the 3,000 to the 1/4 power as well. And this is definitely a calculator question. I do not expect that you would know what 3,000 to the 1/4 is off of the top of your head. So now I would pull up my calculator and I would type in, and it doesn't matter if you have an 84 or an 89 or whatever model, type in 3,000 raised to the 1/4 and you will get 7.401. I'll tell you where to round, right? But there is your answer. So they're not too bad. Okay, now the second one, x to the 2.5 power. Before you solve for that one, you need to isolate x. So of course, we're gonna divide both sides by 6. And you get x to the 2.5 equals 15. Okay. 90 divided by 6. Now, how do you get rid of a 2.5 power? I'm gonna raise it to its reciprocal. So if I raise this to the 1 divided by 2.5, then I have to do that on the other side to keep it balanced. Okay, so then you pick up your calculator, because I don't know what 15 to the 1 over 2.5 power is. So I type that into my calculator, and you get 2.95. So there is your answer right there. So they're pretty quick solving, but you're gonna have to wrap your head around the difference between, these power functions and then these exponential functions. So spend some time looking at those. Okay, the last question then is probably the big grand finale, a little bit of a brain buster. So you're gonna solve this one for x. Okay, and I want you to look at the second the parenthesis quantity. You have 8x raised to the 2/3. And I just got done telling you, when you have a power property, you have to be so careful that you would recognize this is distributing to both the x and the 8. Okay, so if I rewrite this, I have 6x to the 2/3. Then I have minus 8 to the 2/3 times x to the 2/3. And that looks a little awkward, but that is what it's equivalent to. Okay, if you go back up, I'm going to come back to this, but if you go back up here and you just say, oh, look, it's both x to the 2/3, I'm just going to take 6 minus 8, which is -2, you're going to get that wrong because it's actually 8 to the 2/3. And this one is really tricky because of that. So as of now, these two aren't quite like terms. Well, they are, but I have to figure out, 8 to the 2/3, that's such an awkward number. Okay, so if you pick up your calculator, we'll get into more details about how this works later, but if you pick up your calculator and type in 8 to the 2/3, you're gonna get 4. Okay, so you definitely need your calculator for that right now, unless you recall how to deal with fractional exponents, and we'll cover that in the next lesson anyway. So if I rewrite this, again, on my calculator, I typed in 8 to the 2/3 and I got 4. So that's really just 4. And you can double check, please do double check on your calculator. And now I have like terms. I have 6 of these minus 4 of these, which would be 2 of these. So be careful, your like term of x to the 2/3 stays the same. And now I'm just solving for x. So divide both sides by 2. And 32 divided by 2 is 16. Okay, then how do you get rid of a 2/3 power? And that's our whole reciprocal idea. Okay, so I'm gonna just write this step down. So I'm gonna raise both sides to the reciprocal of 2/3, which is 3/2. Because what is 2/3 times 3/2? It's 1. So now I just get x. I pick up my calculator and I type in 16 to the 2/3, and you should get 8. But please, again, make sure you can type those into your calculator. If that's an issue, we should figure that out for sure. Sorry, you don't get 8, you get 64. Woo! That would be bad. Then you'd really wonder what you're doing wrong. So 16 to the 3/2 is 64. More on this later. The answer is technically plus or minus. We're going to get into more details about that in the next several days. So for right now, if you can algebraically get to 64, that's fantastic. More details on why it's plus or minus later. All right, so your homework for 4.2 is just book questions, so page 200 and questions 1 through 6 and 13A. So you can complete those book problems and submit your work on Schoology.